Now, so far in this course, we've talked about statistical significance in two different places. We talked about it in conversion marketing. Was there a significant difference between two or more groups on some variable? We talked about it with the correlation coefficient as well. And here we're going to actually talk about it in the context of this entire model. So the idea that, can we say, are these variables predicting whether or not somebody is pregnant in such a manner that is better than chance alone? So the specific language on how you would interpret this, again, is the same way that you would think about it with conversion marketing or significance, right? So if we just imagined that in the population, none of these variables, or when you put all these variables together in the population, they would not predict whether someone is pregnant. It would just be complete noise in terms of whether or not someone is pregnant. If that were the case in the population, what are the chances that we would have gotten such and such level of an R-squared value? So that is the interpretation of it. So how do we actually get that? So let's go over here to column Z. And in column Z, we need to know how many people there are. And we know that we had 1,000 people that we used to train the model with. And we need to know how many model coefficients there were, or that is how many independent variables that we had, and we had 20 independent variables. And so the degrees of freedom, is equal to how many people in your study minus how many model coefficients there are. And we have 980 there. And then to get the F statistic, so remember we've computed a T statistic before, and when we did t-test, we computed an F statistic when we did analysis of variance. So here's the F statistic again. It's the same F statistic that we saw when we did analysis of variance. We're just computing it in a slightly different way now. So the way we get that is we put equal sign, and we are going to put the explained sum of squares over the sum of squared error. All right, with me so far? And put that in parentheses, and we will multiply that by the degrees of freedom over the number of model coefficients minus 1. And we should actually put this part in parentheses to make sure we get our order of operations properly completed. Let's close that parentheses and click enter. So our F statistic is 39.52. Now remember when we did the t-test and when we did the correlation coefficient and when we did the chi-square, we went to a table. So I pulled up like PDF files on the screen and looked at a table, and we were able to scan down the rows and columns and figure out whether we had gotten a significant value and look up a p-value. So here we're not going to do that. We're actually just going to use an Excel function to do that. So if we type in equals fdist and then open parentheses, and we put in that f value there, that's in cell Z4, and we put a comma here, and we're going to put the degrees of freedom in there, minus 1, and we will put another comma here, and then, or excuse me, that wasn't the degrees of freedom, that was the number of model coefficients minus 1, and then we'll put in the degrees of freedom, end parentheses, click enter, and that's going to give us our p-value. And remember, the lower the p-value, the less likelihood that these results are due to chance alone, assuming that there's no relationship between those independent variables and the dependent variable out in the population. And so you can see we've got this 4.9 something times 10 to the negative 107. So that's like a 0.000. There's like 107 decimal places before you even get to the decimal point. So we know that's like a super low number, so we can conclude that this model is significant.